Good morning, everyone. My name is Maryam, and today I'm going to present our work on leveraging social networks for well-being and health prediction. So the well-being indicators that we have considered in our work are mood or emotion and sleep. In the interest of time, I'm only going to focus on emotion in today's talk. So emotion is a multidimensional entity, and two aspects that we have focused on in our work are happiness and stress that people experience in their day-to-day lives. And this is important because there are a lot of mental health disorders that are closely associated with emotion dysregulation. And if emotion can be tracked and interventions can be provided in time, these disorders can be helped. Moreover, this work can also help with machines that incorporate affect in their operation to provide a better user experience. Now, the next important question is, how do we measure emotion? So unfortunately, there is no device or sensor that can tell you how happy you are or how sad you are. However, there are data sources from which we can try to learn about emotion. So there are three sources that we have considered in our work. So the first one is EMAs or surveys that are designed by the psychologists, and these are questionnaires about how a person is feeling. And since the person who is actually feeling that emotion is telling us how they are feeling, they are very accurate and very informative in their raw form. However, they have a higher user burden. User has to fill those questions. And therefore, they are very expensive to collect and cannot be collected at a very high temporal resolution. Then we have the mobile and wearable sources, which are less obtrusive compared to EMAs. But then again, they are not very informative about emotion in their raw form. Also, they are noisy. However, they are very cheap. They're easy to deploy, and they can collect data at a very high temporal resolution. Now, in order to leverage these sources to learn about emotion, let's take a look at the emotion itself, which is a very complex entity. So there are two aspects. First of all, emotion depends upon and is reflected in the internal dynamics of the body, such as skin temperature, blood pressure, and so on. And we categorize, or we call this the physiology of the person. The next thing that impacts the emotion is the surroundings. And we call them external dynamics, and we use two factors to characterize the external dynamics. The first one is the weather, and the second one is the social interaction. So the social interaction is very important because the phenomena, emotion contagion, tells us that emotion can transfer from one person to another. There was a study conducted with over 3,000 participants over a course of 20 years that showed that people who are surrounded by happy people and those who are more central in the network have a higher probability of being happy in the future. So we have tried to integrate this notion of contagion in our prediction model, and in order to do so, we have modeled social interactions as graph networks. Now I'll present the overview of the framework that we have designed. So first of all, we look at the surroundings of the system of a user, and we call them the external dynamics, and we call them the spatial aspect of the data. So there is a user and he's surrounded by other users. So we have the graph aspect. Then we have the user's own data, such as physiology, and we try to extract the temporal trends from them in a machine learning architecture. And the end goal of the system is that we want to predict the well-being labels of all the users who are part of the network. While we are designing this system, we have tried to ensure that we are not incurring additional costs in terms of surveys or more questionnaires or EMA burdens. I also want to highlight here that the EMA, which is used as a ground truth, is collected at a much lower resolution than the mobile and wearable data. So we often have to downsample the mobile and wearable data, and using graph networks extracted from that data is a very good way of utilizing it further. Now, the first step of this system is how do we create graphs from the mobile data that we have. So we design a dynamic connectivity extractor that takes mobile and SMS data and gives us dynamic graphs of who the user is interacting with over time. So a graph is represented by these circles that are nodes or users in the system, and we represent them as V. And the connections between those nodes are represented by edges E. For mathematical simplification, we represent a graph by a matrix A, and each row and column of this matrix is a user. So Aij, which is the entry at ith row and jth column, tells us the connection between user I and user j. So if it's 0, it means there is no connection. If it's non-zero, it means there is an edge, and W represents the weight of that edge. Now to extract these weights, we have used the call and SMS data. So we sum the duration of calls between two users to get this call data, and for SMS, similarly, we have weighted sum of the SMS that are exchanged between two people. And at the end, we normalize these matrices. I again want to highlight that we are not using the content of the call or SMS to avoid any privacy concerns. It is only the calls made between two people. Now, the next question is, how do we use these graphs to predict emotion? So the graph matrix that I showed earlier is permutation invariant, which means that the location of the users in the matrix do not make a difference. However, neural network is not permutation invariant. It would treat a permuted A as a different sample. So this issue is mitigated by graph convolution networks, which is an architecture inspired by performing convolution on the graphs. And what it does is that before applying a weight, which is learned during the training process, it aggregates features from the neighbors of a user. So let's look at this example. So the figure on the right, when it is trying to perform aggregation for the user shown in black color, it is only going to look at its first hop neighbors, which are in blue color. So it is going to look at the user's data and its neighbor's data. Then if we have a multi-layer GCN network, in the next layer, it is going to actually look at the second hop neighbors. And as we have a deeper network, we are looking farther away in the network for aggregating the information. So that was for the spatial aspect. Now let's talk about the temporal dynamics. Because we know that the past few days of data would lead to a certain state that a user experiences at on the current day. So instantaneous values of, let's say, heart rate or physiological features are not very informative. However, if we look at them as a sequence, they do provide us a trend. So in order to exploit this trend, we have used the LSTM architecture, and we characterize it by the sequence length, which is how many days are we looking in the past to get a prediction in the future. So this is a big overview of the architecture. So we have a module that is collecting information from multiple users, and we call that the GCN-based user data aggregation. We have another module for the temporal trend based on LSTM, and then we combine them and get a prediction. Now, a key issue with this architecture is that it requires both user input feature matrix and the graph. And since we require the graph, as an input, it fixes the size of the network that the model can work on. So maybe the model is trained on a certain data, but in real life, it might get graphs that are not of the same size. Also, with the experiments that we conducted, these are all user-centric studies. So we don't have a lot of participants. However, when we have them for a very long time, they do drop out, or new participants join in. So this connection is very dynamic over the time. Also, some users could be missing their feature matrix, so we cannot use them, and we might have to discard the entire graph. So to fix this issue, we propose this solution called JED, abbreviated as JED. And what this algorithm is doing is that it is taking a set of varying size graphs and transforming them into the required fixed network size graph without losing any nodes or any connections of the network. So in order to design this solution, we have used the basic principle of the GCN that I explained earlier. So that principle is that for a given user, only directly or indirectly connected nodes would contribute to its prediction. So if there is a node that is not connected, it is never going to contribute to its prediction. Now, in order to exploit this principle, we have used a graph characteristic called connected component. So a connected component of a graph is a subgraph in which all the nodes are connected. So based on these two tools, we have designed this algorithm where first we extract the connected components. So as you can see in the figure, there are two connected components. Now we process these components through a set of three conditions. So the first one is if the size of the component is equal to the required size. We just put it in a container called main container. If the size is less than the desired size, we put it in another container called the remaining container. And if the size is bigger than the required size, we break it into the required sizes graphs, and the remaining graph is put into the remaining container. So at the end, we process the remaining container by combining graphs and getting the desired sizes. So once the system has been designed, we are going to conduct a series of experiments. And the objective of these experiments is to quantify the gains provided by integration of the graph in the prediction model. So first of all, we have the proposed model that I showed earlier as well. In order to achieve this objective, we use the benchmark where we replace the GCN layer by a simple convolution layer. So a graph is not provided, but there is still some aggregation happening. And finally, we have a very simple LSTM-based model, which is often used in the literature. So for the experiment, we have used the snapshot data set, which was collected by my advisor and the co-author of this work, Dr. Sano, during her stay at MIT from 2013 to 2017. There are 4 sets of features: mobile, physiological, weather, and survey data. After cleaning and pre-processing, we had 206 features, 206 participants and 314 features. We pre-process the data into 3 steps. First, we impute the missing data, we remove the outliers, and then we normalize the data. We have a train validation test split of 50, 10, and 40. So for the stress and happiness scores, they were over a scale of 0 to 100. So we classify them into low stress, high stress, and moderate stress, and similarly low happiness, high happiness, and moderate happiness. We had an imbalance in the classes in the data set, so we used micro F1 score as an evaluation metric. And finally, in order to accommodate for the sensitivity to the initialization and the test train splits, we repeat the process multiple times and take the average and do a statistical test to show that they are significant. So these are the overall results of our model. So as you can see that the proposed model has a higher F1 and a lower RMSE compared to the others. It works better than the convolution, and the convolution works better than the LSTM. Also, the proposed model has a much lower standard deviation in the results compared to the benchmarks. So this was like a very average overall performance. So we also dived into to look at how the model parameters impact the performance. So for this purpose, for the first figure, what we did was we fixed the memory, which was 5 days. So we are looking at the past 5 days of data to predict tomorrow's stress or happiness. And we varied the size of the network. So we saw that as the network size increases, the proposed model and even the convolution model improves in performance, but LSTM degrades because there is no aggregation mechanism provided to it. Similarly, in the next experiment, we fixed the size of the graph and changed the temporal memory. So again, with increasing data, increasing memory, the performance is improving for the proposed models. However, initially there is a boost, but then there are diminishing returns. Another thing that we looked into was that different parts of the network would experience different prediction because some are more connected or some are more influential than the others. So we tried to explore the relationship between the model error and the network topology. Now for characterizing the network topology, we use influence of a node. And to do that, we use the centrality of the node. So there are multiple definitions of centrality. The 4 definitions that we have used are degree, closeness, eigenvalue, and page rank. In order to explore this relationship, we use the statistical model using generalized estimating equations. We customize the model based on the personality traits that were identified, the groups identified through the personality traits. So first of all, we noticed that eigenvalue centrality. So this tells us that the node is important if it is connected to a lot of influential people in the network. So a higher eigenvalue centrality means that you're connected to more influential people in the network. So when the eigenvalue centrality is higher, we have a higher error actually, because we are aggregating information from a lot of nodes that might not be very important. Secondly, when the degree is small, which is less than 4 direct neighbors, actually higher direct neighbor means that lower error. However, when the degree is very large, we do not see any kind of trend because sometimes it improves the performance, sometimes again there is aggregation from irrelevant nodes and that's degrading the performance. So I'm going to conclude my presentation now. So first of all, we observed that integration of graph networks do help with the prediction of emotion. The way graphs are constructed is important, as I showed that certain topologies work better than the other. Also, when we designed this architecture, it was to predict the emotion for all the users in the network. So this architecture is very friendly for doing research in macro scale contagion, if we want to investigate contagion or the emotion behavior of a very large network. It is also helpful to identify nodes that are important. So we can only collect EMA or survey data from those important nodes or influential nodes and do a characterization for the entire network. Finally, we created graphs from call and SMS data, but social media data could be used to have dynamic graphs. And also we conducted similar set of experiments for sleep behavior as well. And we observed that integrating contagion or graphs in sleep also gave us a better prediction of the sleep behavior. So I'll take questions now.